And hello everyone, welcome back to Turbulence modeling. We're going to continue the theoretical background discussion. Today we're going to talk about the Allmaras improved delay detached eddy simulation, or SA-IDDES for short. So what is this basically? The long and short of it is that it's a combined model of warm modeled LES and DDES. So it's a hybrid of another two models that we are already familiar with. So before I begin, I'd just like to go through some of the references where you can find this paper on. You can go to Google Scholar, okay, and you find this link over here. They'll tell you, okay, where is this paper coming from? And then this is the citation for it. The paper is named A Hybrid RANS LES Approach with Delayed DES and War Modeled LES Capabilities. You can also find this on ResearchGate. You can find this on ResearchGate, and you should be able to download the full text PDF without any kind of requirement or subscription. So this will make it very easy, at least for us to access the material there and look into the paper more in depth. Alright, so this is available on ResearchGate, and of course if you are interested in the source code and you see how this is applied in OpenFoam, here is the source code over here. Alright, and you will see two files. You'll see of course the C file and the H file, and in the C file, if you look at the C++ code, here are the values of this is the code, and these are some of the values of the constants that they use. And last but not least, at least a tutorial case is available in OpenFoam. It is called OpenFoam V in the OpenFoam V1812. This is inside the validation of turbulence surface mounted cube. This is the link for it. You can go and take a look. It uses the Spalart Allmaras IDDES model. So moving on, let's discuss some of the things that are unknown first. We know what DDES is. Just want to clarify what war modeled LES is. So I'm going to clear all of these up, and I want to start with our usual balance of our usual pictograph of or picture of our turbulent flow profile. We have our boundary layer, and then we have the free shear zone. You should be quite familiar with this now. The boundary layer and the free shear zone. The boundary layer is roughly, you can cut it up into 2 or 3 regions. If you want to be really precise, you can do up to 5 regions even. But you have basically the viscous sublayer. You have some buffer zone. And you have a lock law region. Alright, so let's do something we are familiar with first. What does the DDES intend to do? Okay, for DDES, alright, we intend to use the RANS model here, Reynolds average Navier-Stokes here. Anything above, okay, for DDES, anything above we want to use LES to resolve our eddies. That's the basic idea of DDES. Now, okay, let me move this here, and then let me move this here. Okay, and okay, question is what is war modeled LES? War modeled LES is basically this. Okay, we have, let me use blue instead. Let me draw this. Okay, instead of using LES only in the free shear zones, we want to use LES more than in the free shear zone as well. We want to use it, okay, in the boundary layer as well. So wherever you have turbulence here, Here you can use LES. And of course, anywhere here you can use your RANS model. Okay, so the RANS model will be used here in the buffer zone, or especially in the viscous sublayer. Alright, this is where your RANS model will be used for modeling this wall viscous region. Anything above, you use LES to resolve. Okay, LES to resolve in the free shear zone and in the boundary layer. Of course, you can actually do some RANS over here also. There will be a transition region somewhere here in the log law buffer zone region. Yeah, but the idea is that the influence of LES, the key difference is that the influence of LES actually penetrates into the boundary layer. That's what wall modeled LES is about. So you'll see this in literature as WMLES. So this is the picture I want you to see. Okay, so I asked the question, you know, can DES be used for LES mode in boundary layer? So this is wall model LES, and one of the interesting findings was that if you use the DDES equations and you put it in the right grid, you can almost do wall model LES. And of course, you make some tweaks to it. You can do wall model LES, right? Just like you can use, in a way, you can use the Spalart Allmaras model. You just give it a little tweak and then it becomes the DES model. Okay, so likewise, you can use a DDES equation or DES equation. You tweak it a little bit. I mean, most of the equation is constant. You just tweak it a little bit and then you get the wall model LES equation. Same idea, where you can so-called recycle. The idea is that you can recycle some of the equations and, you know, put it into other models, even though these models are pretty much fundamentally different. Now I know some of you might be familiar with the Weyl equation. Okay, the Weyl equation. Okay, so this does wall modeling. This wall adapting local eddy viscosity. This is strictly LES. It's LES only. So if you're wondering how this differs from the wall model LES, okay, both of them, yes, they have a model for the wall. For wall model LES, they use the RANS model. For wall adapting local eddy viscosity, there's no RANS over here. Okay, let me use the green. No RANS. Okay, instead we just use a mathematical function. We use a mathematical function to damp okay, mu t artificially. Okay, so if you take a look at this website for wmles.umd.edu, you will find this comment being said over here. It says, in contrast, there have been almost a few handful attempts at wall model LES as a purely mathematical exercise without appeals to physics, including the use of control theory, blah 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 blah. Okay, this guy Nikud, I'm not sure how to pronounce his name. This guy is the same guy who did the, if I'm not wrong, he's the same guy that did this Weyl model. So if you search on this Google Scholar, I mean, you'll be able to download the wall adapting local eddy viscosity model. Okay. Okay. You see this guy, F. Niku. I'm not sure how to pronounce his name. It's the same guy as over here, F. Niku, the same guy, and F. Ducros. Well, he's not here. You will see. Okay, it's just that this Ethnicud guy. So you will see his name over here, and again it's about to deal with LES type flows. So Ethnicud, yeah, he's the guy in charge of the wall adapting local eddy viscosity model. So these are likely, based on empirical functions, nothing too much more than not too much theory here, and definitely no RANS. There's no RANS model. Okay, so unlike whale, Bohr model eddy viscosity, Bohr model LES uses a RANS model for viscous sublayer, alright, within the boundary layer. Okay, Will just uses its own in-house damping functions, which are kind of corrected. Alright, so this is the key difference between these models, or one of the differences I consider more important. Okay, so yeah, question is, can DES be used in LES mode for boundary layer? I mean, in theory you could, but you actually run into some problems. Okay, and again, I say again, this is different from the whale model which we discussed earlier. It uses an empirical function in the viscous sublayer, but not RANS. Okay, so you can do it, but there are some problems actually. One problem is called this thing called log layer mismatch. Okay, so what is a log layer mismatch? Alright, so let's have our u plus against y plus plot. Alright, and you have the u plus, your viscous the sublayer equation, u plus equals y plus, and then we'll have the log law region, which is u plus equals to ln, okay, or rather I can use this von Karman coefficient here, ln y plus some constant, right, plus c. So the whole trend is you're supposed to follow this trend. You follow this trend in the viscous sublayer, then you have this buffer region, then you follow the log law. There, of course, there's a log plot over here, so this isn't linearly plotted, but this is the general shape of the curve. Now, yeah. So remember, in the inner layers, you use the RANS model, right? You use RANS model here for wall models LES. Wall model LES. Okay, for wall model LES, you have this RANS layer inside, and then you kind of slowly transition towards LES over here. Alright, you slowly transition towards LES, so there will be some transition zone. Okay, so there's some transition zone over here. Alright, so I don't know how long this transition zone is. Depends on the flow, and the damping function, what have you not. The blending function, sorry. Depends on the blending function. Okay, but the thing is that in the log law region, you have your initial part being simulated by RANS equation. Then you slowly transition into LES. Okay, the thing is, LES can simulate the log law region, but one of the problems was that you still have u plus equals 1 over k ln y plus another constant, right? However, the constant here, we call it C2, and then in the Reynolds average Navier-Stokes part, it'll be C1. So maybe I just put RANS here. Then I'll just put I'll put LES here. Okay, what they found was that, this k is was actually equals to this k, so that's okay. Right, this gradient has been preserved, but what they found was that this C-rens and this C-LES, okay, C-rens, when they do the full simulation, it was not equal to C-LES. Again, part of the reason was because there was this drop in nu t, and it was not sufficiently made up by the eddies. Eddies didn't make up for the drop. Okay, not enough. Okay, the eddies weren't enough to make for the drop in nu t. So what they found was that, okay, you have this problem where you have both of them having a log law kind of profile, but these constants are not the same. So this is actually what is known as the log okay, in the paper is known as a log layer mismatch. Okay, so this is the Rens bit, the log law produced by Rens, the Reynolds average Navier-Stokes. This one's produced by LES. Okay, both are not equal, so that's a problem. That's the log layer mismatch. So there was some tweaking that needed to be done. Yeah. So there's some tweaking that needed to be done, and you kind of have to adopt a correct blending function for the wall model LES. Okay, you need to adopt a correct blending function for wall model LES. What's the effect of this log layer mismatch? You actually have a 15 to 20% error in skin friction. So that means the drag coefficient, for example, for a plane wing can be off by that much, because skin friction correlates directly to the drag coefficient, for example. So this is actually too much error for aerospace application, according to the authors of this paper. They are Shur, this Michael Shur. Okay, looks like it's from Russia. If you look at the paper, and then Spalart is there and Strelets is there. Strelets is the guy who did the K omega SST DES model, if I'm not wrong. Okay, but no matter, you see the guy Spalart in this paper again. Alright, so you have to adopt a correct blending function for WMLES to prevent this log layer mismatch. And what does it look like? Well, what does WMLES look like if you were to use the Spalart-Allmaras model? For the Spalart-Allmaras model, okay, so similar to DES, because both are hybrid methods with different intents, of course. Similar to DES, we just change the length scale and blend it with some complicated looking empirical functions. Okay, so remember both DES and WMLES, these are hybrid methods between Reynolds average Navier-Stokes and the LES model. It's just that the wall model LES has a heavier dependence on LES than this DDES. Meaning to say, wall model LES has a higher percentage blend, so to speak, of LES. Okay. So if you recall the length scale for DDES, it's as such. It is the length scale for DDES equals to L Rens, the Reynolds average Navier-Stokes length scale, minus FD. We discussed what FD was in the last video or last few videos. Yeah, it's somewhere here. I don't want to go through that again. Yeah, but these are again blending functions, right? Blending functions. Right. So I'll just, yeah, if you want, you can go back and take a look. I'm not gonna go through it again. So Yeah, remember this FD is the stuff that delays this onset of DDES. I mean, this delays the onset of LES in the boundary layer. So that's why you have that there. It's the hyperbolic tangent function. You will find it in the paper as well for the IDDES. Okay. If you want a wall model LES, it is constructed a very similar way. You have a blend between the Reynolds average Navier-Stokes and the LES length scale. You have FB, which switches between 1 and 0. So it tells you, okay, I want to switch between the Reynolds average Navier-Stokes and the LES. So FB equals to 0 will imply LES switch on. FB equals to 1 implies the Reynolds average Navier-Stokes switch on. So this is the behavior of this. Now you may be wondering what this 1 plus FE is here for. Now this 1 plus FE, this 1 plus FE is here actually to help correct this log layer mismatch, because you have this this transition from RANS to LES, and then this new T drops too much, and the eddies in the resolved LES layer, resolved meaning to say, okay, you can actually see the velocity. The CFD software actually solves for the velocity field and all the eddies. So the eddies which you see in your CFD simulation, which are not part of the turbulent viscosity, these are resolved eddies. Okay, these are eddies you can actually see in your simulation. So, and they are part of your velocity field. So the resolved eddies do not make up for the drop in this new T. So what we have is a what do you call that? 1 plus FE, similar to our booster function or whatever. Okay. Regardless, this is here actually to just help with this log layer mismatch, to kind of slow down your decrease in new T enough so that you don't have this log layer mismatch problem. That's what it's there for. So let's go through FB and what it looks like. Okay, FB is pretty straightforward. It's an empirical blending function to switch between the RANS and LES length scale. Okay, again, FB equals 1 is the RANS mode, FB equals 0 is the LES mode. And I'll stop here because it's 22 minutes, and I'll continue discussion in the next video. Thanks for watching. I'll see you guys again.